we now know how to name aldehydes and ketones. And what I want to do in this video is show a mechanism for actually creating one. And in particular, we're going to create a ketone. So let's say we've got ourselves some benzene. And in the first step of this reaction, the benzene is just going to sit and watch. We've got some benzene, and we've got some acetyl chloride. Acetyl chloride. So it looks almost like an aldehyde or a ketone. But instead of having a carbon chain here or a hydrogen, we're going to have a chlorine atom right over there. So this is acetyl chloride. Acetyl chloride, sometimes called acyl chloride. This is acetyl chloride. And we're going to have an aluminum chloride catalyst. And a catalyst means that it participates in the reaction, but it enters the reaction and it exits the reaction. It is the same molecule. So it just catalyzes it. It doesn't disappear. It just changes halfway, but then goes back to what it was before. So we have some aluminum chloride, and it's bonded to 1, 2, 3, 1, 2, 3 chlorines. Now, the first step of this reaction is to turn this acetyl chloride into a good electrophile. Turn it into something that's really good at nabbing electrons, so good that it can break the aromaticity of the benzene ring and essentially add itself to the benzene ring. This is actually the same mechanism we saw with, I think, electrophilic aromatic substitution. I always have trouble remembering the names, but I always imagine it's electrophilic substitution. Either way, it's this very similar mechanism. And actually, what we're going to show in this video is called Friedel-Crafts acylation, because this right here is called an acyl group. This right here is called an acyl group. And we're essentially going to acylate the benzene ring. We're going to add this group right here to the benzene ring. So enough of what's going to happen. Let's actually see it happen. So the first thing to realize, this aluminum chloride, the aluminum in it is electron deficient. At a first cut, if you just look at the periodic table, you have these chlorines over here, pretty electronegative. Aluminum is in the same row, but chlorine's way more to the right, so it's more electronegative. So the chlorines are going to hog the electrons in this molecule. The chlorines are going to hog the electrons, so the aluminum is going to have a partial positive charge. Chlorines will have slightly partial negative charge. On top of that, you see aluminum is a group 3 element. 1, 2, 3. So it has 3 valence electrons. You see that right here. 1, 2, 3. Nowhere close to the magic number of 8. Even when it covalently bonds with these chlorines, it can only pretend like it has 6 electrons. It can kind of pretend like it has these chlorines electrons over here. But that only gets it to 6. So it would really like to have more electrons to get closer to that, magic 8 number. So what you can imagine is a situation where this chlorine on the acetyl chloride, this chlorine, it's already hogging this green electron from this carbon. It was already doing that. It's more electronegative. So this thing over here will actually be given to the aluminum. And so it will then have a bond with the chloride. So if that happened, what does our reaction look like? So if that happened, what does everything look like? Our aluminum chloride, or what was formerly aluminum chloride, now just gained an electron, and with it, it is now bonded to another chlorine. So it is now bonded to another chlorine. And since it gained an electron, let me make it very clear. This is an L. My penmanship is deteriorating. That's an L. And since this aluminum gained an electron, it now has a negative charge. And normally a negatively charged thing isn't that stable, but these guys are electronegative, so they might hog a lot of that negative charge. And on top of it, aluminum can now pretend like it has 8 electrons. It has 1, 2, 3, 4, 5, 6, 7, 8. When you covalently bond to someone, you can kind of pretend like you have their electrons as well. So now you have this anion that was formed from the aluminum chloride. And now the acetyl chloride will look like this. The acetyl chloride, let's scroll down a little bit. And let me make it clear. We're in the next step of the reaction. We are in the next step of the reaction. What was formerly the acetyl chloride has now lost the chloride. So it's now really just a acyl group. So you have the carbonyl bonded to a CH3, a methyl, just like that. This guy lost his electron. So now he has a positive charge. And this is actually, it's not that stable. And you're going to see it's actually highly reactive. It's a very good electrophile. It wants to steal other people's electrons. But it can exist for a short amount of time, especially because it is resonance stabilized. You say, how is it resonance stabilized? Well, this oxygen over here has 2 electron pairs that I didn't draw before. and let me draw the second one in a different color. It has 2 electron pairs like that. So you can imagine a situation, the electron, this carbon is already, he has a positive charge, and this oxygen is more electronegative, is already hogging his electrons. Maybe he wants to give back a little bit. Say, hey, this is positive. These electrons, all of the electrons are hanging out here. They'd be attracted to the positive, and you can imagine one of these electrons being given back to the carbon. And if that happened, then we have another resonance form. We have another resonance form that looks like this. So this was our original molecule, or that's our original, or what it looked like. We still have this double bond right over there. But now this, or that pair of electrons, now this pair of electrons now forms another bond. This electron over here is now on the oxygen end. This electron over here is now on the carbon end. And now they have a triple bond. And what happened? This positive carbon gained an electron, so it's now neutral. And the neutral oxygen lost an electron, so it is now positive. And you can imagine this is not a very stable, that you wouldn't see this just floating around by itself, but it does stabilize this entire configuration. It stabilizes this molecule. So you can show that these are alternate resonantly stabilized structures right there. But as I said, these aren't super stable. This guy really, really, really wants to react. And now this is where benzene comes into the mix. And actually, let me draw a little dividing line here, just so we know that this was a separate stage of our reaction. So that was the first stage. Then we go over here. And now benzene comes into the mix. The benzene was floating around. So we have our benzene floating around just like that. And then I'm going to draw one of the hydrogens on one of the benzenes. All of these on one of the carbons. All of these carbons have hydrogens on them. I just won't draw them all. It just makes things complicated. But this guy, we said, is a really good electrophile. And you have to be a really good electrophile to attract electrons from a benzene ring to break its aromaticity. But if it bumps or into this guy in just the right way, just the right angle, you could imagine that this electron on this carbon right here gets swiped by the acyl group. Gets swiped by the acyl group. So then what do we have? So now I will go back in this direction. So you have what was a benzene ring. So what was a benzene ring? It still has, we could draw the double bonds here and here, here and here. And we, of course, have this hydrogen. We have this hydrogen. But now this bond, which was the double bond there, is now bonded to the acyl group. So it has that blue electron that the acyl group nabbed. And let me draw the acyl group. And I'll flip it over. I'll flip it over so that we have the methyl on the right-hand side. So it's a carbonyl bonded to a CH3. It was positive. It now gained an electron. It is now neutral. It is now neutral. This carbon over here lost an electron, so it is now positive. So it is now positively charged. Now, we mentioned the aluminum chloride is a catalyst, so it won't just sit around there as the anion. It has to go back to being aluminum chloride. So let's bring the aluminum chloride back into the scene. So we have our aluminum chloride. Let me copy and paste it. Copy and paste. So we have our aluminum chloride here. And so you can imagine that the benzene ring wants to go back to being aromatic. So this electron right here, on the hydrogen, might really want to go back to this carbon right over here, this carbocation. And at the same time, if this anion now passes the hydrogen at just the right angle at the right time, while this guy is attracted to this carbon, this chlorine can give this green electron to the hydrogen nucleus, which is really just a proton. And then the hydrogen's electron can be taken up by what was this carbocation. And then what did we have? Then we have a situation where our benzene ring is reformed. We have the aromaticity again, where we have that double bond, and now we have this double bond again, although now it's using the electron from the hydrogen. And now we've substituted this hydrogen, which is essentially this acyl group. This acyl group right over here. So we have a carbon double bonded to an oxygen, bonded to a methyl group. And now the aluminum or this anion lost its electron, so it goes back to just being straight up aluminum chloride. Aluminum, it goes back to just being straight up neutral electron deficient aluminum chloride. And we're done. We've just acylized this benzene ring. And that's why this mechanism is called Friedel-Crafts. Friedel, Friedel, Friedel-Crafts, acylation. Acylation. And Friedel is actually a former president of MIT, and I did some reading on this. And he did not have a PhD, but because he discovered Friedel Crafts acylation and this Friedel Crafts actually alkylation as well, they said, hey, this guy's a smart dude. Let's make him the president of MIT. But I just wanted to show you that this is a reaction for creating a ketone. So this ketone that we've created is acetophenone, which we've seen before, which we learned is a common name for this molecule that we learned in the first ketone video. And I'll write it in purple. Acetophenone. And we're done.